Welcome to Coding Adventures. In today's episode, we're gonna implement these googly eyes that follow the mouse cursor. This is such a fun project, and it's probably the smallest coding project that we implemented here on the channel. We only need to know a little bit of math, and then the coding is probably done in about 50 lines of code or even less. So this is in continuation of yesterday's project, the one with the analog clock. Therefore, without further ado, let's begin coding. Alright, welcome back. So I'm here in my code editor. We're gonna write the JavaScript program to implement this eyes that follow the mouse. But before we actually start coding, let's start with a little bit of planning on our notebook. So I hope you brought a notebook with you if you want to take notes. In my case here, I'm gonna just draw and plan a little bit this small program. So let's visualize here what we want to create, to implement. I'm gonna draw the canvas, and as you know, the canvas in the environment that we are using, it's 800 by 600 pixels, with the origin in the top left corner here, and the x coordinates go to the right, and the y coordinates goes to the bottom. All right, so we want to implement these googly eyes that follow the mouse cursor, which are nothing more than two circles. And perhaps the mouse cursor, let's say it's here somewhere, and these eyes are looking at the mouse cursor. So basically the pupil of the eye, these parts, should basically be oriented something like this. It's like they are looking towards the mouse cursor. As you can see, it's all about drawing a few circles on the screen, and these ones are kind of fixed. The only difference is in these inner circles that should change the position as we move the cursor around. So if we move the mouse cursor this way or that way, this circle should basically, it looks like a cat. This circle should move around on the canvas. All right, so how can we do that one? And I said that this one is similar to the program that we implemented yesterday, the analog clock, and that's because in both programs we are basically doing some transformations from the Cartesian system of coordinates to the polar one and back. And actually yesterday we converted from polar system of coordinates to Cartesian, and now we're gonna do the opposite way. So let's remember what we did yesterday. So we said yesterday we converted from polar, which nothing else but basically saying we converted from an angle to an x and y on the canvas. So we converted from polar to Cartesian. And now we're gonna learn how to convert basically from Cartesian to polar coordinates. And of course, later on we're gonna convert back to Cartesian because we want to display things on the screen, but that's the same thing as the first one here. So what we did yesterday was basically when we implemented the analog clock, we had a particular point, this one, and we knew for this point basically the angle that it makes with the horizontal axis, the theta, and we knew the r. Basically we converted from knowing this distance from a certain point, from a certain origin, and knowing also the angle, we converted that into an x and y coordinate, finding out which are the coordinates of this point. And in this way, what we did yesterday, by varying the angle theta and keeping r constant, of course, we implemented this analog clock, which is basically we made the hand of the clock go round and round on a circle. All right, and refer to the project from yesterday if you want to see this one. Now we're gonna do the opposite. Let's say we know already, we need to figure out the angle. So it's the other way around. Here is the mouse cursor in our case. And what we need to do, we know we need to figure out, we know the x and y of a certain point. Of course, we know the x and y of the mouse cursor, because it's our cursor that we move on the canvas. And now we need to figure out back what will be the distance from a certain point or from the origin to this one, to the mouse cursor. And of course, more importantly, the angle that it makes with that point. And actually, in the current implementation that we'll do today, we'll not use at all the distance or r here. We are not interested in calculating, but we are interested in calculating this particular theta. And why is that? Well, let's remember what we want to implement here. We want to implement that googly eye. So let me draw an eye here, or attempt to draw one, which is a circle, like we said. And let's say the pupil should come in this position when the mouse cursor is here. So in other words, we need, if you notice, from the center of this circle and the mouse cursor here, you can imagine there is a line. And if we are able to figure out what is the angle of this line, so this angle here, theta, we'll be able basically to very easily draw a particular, we don't even have to draw the this line, but we'll be able to figure out what is the coordinate here and then draw a small circle. And that will be our implementation. All right, so a lot of theory. So how can we figure out this theta first? Well, imagine this one is a right triangle here. So from the mouse cursor that we know it's at x and y coordinate, we know this time the x and y. We need to figure out theta. So we know the tangent of theta. Let's write it first this way. Tangent of theta is the opposite leg, which is, let's name this one dy, over the adjacent leg. Let's name this one dx. So that's dy and dx. In other words, theta is the arctangent or inverse tangent of dy over dx. All right, so it's a very, very simple formula, as you can see here. And we figured this out, pretty simple. And now all we have to do is to go into our code and implement this formula, figuring out what is the angle that is made between the mouse cursor and a certain point, which is the center of the eye, and then draw this, make this circle, draw this pupil there. So when the angle changes, we're gonna redraw here the circle. And if the mouse cursor, let's say, go on this side here at a certain point and makes this bigger theta, we're gonna draw here the pupil. And this way we'll have this funny effect of an eye that follows the mouse cursor. But it's nothing else than a simple calculation in the coordinates canvas. All right, so let's see how we implement this one, all this formula in the code. And just for the reference, and I mentioned that yesterday we created the other formulas, actually before switching to this one, like a quick recap, these were the formulas that we basically used when we calculated in reverse from polar to Cartesian. And today we're gonna use this formula to calculate from Cartesian to polar. And as I mentioned that we are not interested in figuring out also r, which is also something that you can come out with easily. But if you want, we can calculate this one as well. It's using Pythagoras in this triangle, or here in coderapid.com or p5.js, this r, we can calculate it using a dist function. But perhaps about this one in another implementation. All right, so I'm gonna keep my notes handy here, and I'm gonna see how to implement this particular formula in the code here. Perhaps before starting implementing the eye, I should implement a small small line that follows the mouse cursor, like a needle. I like to call that one a needle, right? So imagine a needle in the middle of the canvas that goes around following the mouse cursor. So let's do that one. So let's have a function here, display needle. And this needle, we know the x and y. Let's fix the x and y being, let's say, the other end of the needle, and the other end will be the mouse cursor. All right, and this needle will have a certain size D. So again, let me draw here just to be clear what we want to implement before starting with the eyes. Coming back. So we have our canvas here, and we're gonna create in the middle of the canvas, we want to draw a small needle that follows the mouse cursor. We know the mouse cursor coordinates. This time we're gonna use the values that are available in P5.js. So this basically are mouse X and mouse Y. Okay, so these are the coordinates of the mouse. And now we want to draw this segment of length D, we said there. So one end it's fixed at X and Y and has the length D, and it's trying to reach the mouse cursor. It's actually not not reaching the mouse cursor because of the D size. We can move the mouse cursor anywhere on the canvas, but this kind of segment will try to go and follow the mouse cursor, always trying to point at the mouse cursor. So let's start with this one, and then we're gonna see how to implement the eye around it. And as we said, we'll do all this by calculating this theta here, that is dy over dx, or arctangent of that one. Too much talk already. We put so much theory in this exercise. All right, so let's figure out the angle. We're gonna name the variable angle here. And basically the function to do that, we said it's arctangent of dy over dx. And dy, it's, if we are looking really carefully, back to the drawing board here, dy is actually mouse x, mouse y, minus y, and dx, it's mouse x minus x, all right? So, because the angle is the same, even if we are basically elongating this line till it reaches the cursor. So, in this case, we're gonna consider this as being dy and this as being dx. So, we know dy, we know dx. So, let's try to implement that formula in the code. So, we said we can use the inverse tangent or arctangent of mouse y minus y over mouse x minus x. All right. And now we know the angle, and with the angle known, we can convert. So we already converted from Cartesian to polar. We can now convert back to Cartesian and draw that kind of line using the formulas that we used yesterday. So basically, let's remember those formulas. Lots and lots of formulas, but let's remember quickly those ones. So these ones are these formulas. We're gonna determine the point here by starting from a certain point in the center, plus r cosinus of the angle, and then r sine of that angle. I'm gonna write them in the code, and I hope that makes sense for you. So we know already one end of the line. It's at these coordinates. Let's figure out the other one. So let y x2 is basically x plus d times cosinus of angle, and y2 is y plus d times sinus of angle, like this. And now we can draw a line from x, y to x2, y2. So, and you know what? Let's call this function in a loop so we basically can animate it. We're gonna define here the loop function, which is called for us automatically by the browser up to 60 times per second. We're gonna clear the canvas and then say display needle. Let's fix one point of the line in the center of the canvas. And let's say this line has 200 pixels. All right. So let's run it. It kind of moves but jumps around in a very weird way, right? So what causes that problem? Well, that problem is caused by the arctangent function. And let me show you something interesting here. Wikipedia, arctangent 2, all right. Now, in many programming languages, JavaScript included, actually says here, arctangent was first appearing in Fortran. This function appeared in basically each and every programming language since 61 till today, and it's kind of a replacement of arctangent when we are working on a Cartesian system of coordinates. Arctangent 2, we use it similarly to this one, but so we just put 2 here and with one difference. Notice here what's happening if we do this division with arctangent like we used initially. When this one becomes 0, it's division by 0. Also, if you read carefully here, and if you learned in math, probably in the school, if you want to calculate correctly if you want to do the transformation, you also have to consider the quadrant in which the point is. Basically, it's expressed here like this. So, therefore, we are not using arctangent function, but arctangent 2 that takes these two values not as a single value, basically not as a fraction, but actually as two separate values, separated by comma. And arctangent 2 will do the calculation inside. We'll see when this one is 0, not avoid division by 0. We'll also check quadrants and so on and so forth. So you have to check this article from Wikipedia if you're interested in the math, or refer to your math textbooks again for this one. But just remember, each time in JavaScript or any other programming languages, you have to do these conversions from Cartesian to polar, use arctangent 2, not arctangent function. So let's run now the program, and indeed our line is following the mouse cursor. So even if I'm going further away or if I'm coming close, I can basically rotate this line. And this technique is basically used every time you want to orient different objects to the mouse cursor, like this line, or maybe that pupil in the in the googly eyes. Let's also put a circle here at the end to make it a little bit more interesting. 5, like display needle, and let's run it. All right. So now it's a question of how to transform this program into that one with googly eyes. It's just a matter of just drawing different shapes. But let's play a little bit more with this, this needle before that. What if we create not one but multiple ones? Let's do that. Just a simple exercise. Let's create a field of needles that try to reach to the mouse cursor. So let's loop on horizontal. Perhaps x starts from 0, x less than 800. And maybe we should increment in 30 pixels increment, something like that. And let's loop the same y is 0, y less than 600, y plus equal 30. And let's move this line inside the nested for loop. And instead of having a size of 200, which will be too big, let's make it 10 and see how it looks like. Oops. Let's not put the center in the center of the screen, but actually at x and y coordinates. Basically create a field of needles. Let's make them a little bit bigger, perhaps 20 pixels here. And let's say this one looks like magnetic needles to me. Display magnetic needle. And make this small and a little bit smaller. All right. It's an interesting effect. Notice how all these arrows are trying to orient towards the mouse cursor. We could end the lesson here. This is basically a small project on its own. Actually, let me share this one with you. So this one is magnetic needles. Let me share this one on the chat. It's fun on its own, right? Let me go on the chat here. But nevertheless, we said that today we're gonna implement those googly eyes. So let's make a copy of this one and see how to can we transform it into into those eyes. All right. So we don't need all these fours. Let's come back and revert all this code and have just one magnetic needle here. And Oops, X is not defined, of course. It was like this, and a certain size. All right, so perhaps we should name this one draw eye or display eye. And let's display an eye. Actually, we need two eyes, right? So we're gonna call this function twice. And we want to center them on the screen. So this one is not at 400, it's perhaps at 200. And this one it's at 600. I don't know. We can we can change them. But see, already the two needles are kind of following the mouse, similar to the that eye pupil. So let's try to arrange this function a little bit to look like we're drawing an eye. All right. So what we have to do here is to basically draw a circle, and yeah, we'll draw a circle here, right? Circle at X and Y, and this will be the radius. Let's see. All right, we have the two eyes, and now here we don't have to draw this line at all, right? Only the small circle will keep it, but not there, not exactly at the end here, not exactly of length D. Perhaps if we're coming back to the drawing board, let's plan a little bit this one. Let's figure out what will be that kind of distance. So this will be the big circle, and we want to draw the pupil here. This is the center of the circle, right? This one is X, Y. And in the previous case, X2, Y2 was at the edge of the circle, but we need to figure out this one. So we already, let's say this one is following the mouse cursor, which is here. We're already passing this distance D, right? So perhaps here it's at maybe 75% of D, right? And the remaining here, we're gonna use the 25%, we're gonna use it for the radius of the pupil, this part here. Something like that. I think will work. Let's see. So if right now we are placing the circle exactly at the same distance, basically, which is kind of on the big circle here. If we run it again, yep, the small circle is on the big circle, and let's increase a little bit the radius to have fun. Yep. Perhaps if we are drawing frog eyes, it will be more correct to do it like this, but we have other intention here. So let's figure out a second D distance, pupil distance, which we said maybe 0.75% of D, right? And now the second coordinates, this will be PD for the circle. All right, it looks better. Oh, but the radius we hard-coded at 30, we reserved already 25% of D. So should be fine, like this. Let's have it in a variable, like pupil radius is 0.25 times D, or D minus pupil distance. Let's have here PR, and let's see it. All right, let's fill this up. So this one will be filled with black, and initially when we draw the eye, let's have this one filled with white, and run it. And this is exactly what we intended to achieve here. Now we can make this one even more fun if we want. Let's try to make them a little bit less big, like this, and maybe get them closer. 300, 500. They're too far away. Okay, I like this eyes in this way. And now if we want, we can even draw a smaller circle inside this one. Up to your imagination, or we can draw the pupil in different colors or make colored eyes. Let's try to draw something here at the circle. X2 plus PR on 2. and y2 plus pr on 2 and pr on 4, something like this. Yeah, you can have fun with this one. Of course, we didn't orient this one. If you want, you can orient it, but in the same way using a similar formula. So this is the effect that we wanted to achieve. Let me share the program with you on the chat. It's a very small program. We said 50 lines of code. Actually, it's 25 lines of code with plenty of white spaces in between. Nice. And basically with this one, we conclude our today project. It's a very small coding project for beginners. You also learned about converting from polar coordinates to Cartesian and from Cartesian to polar. We went a little bit all over the place with the theory, but I still hope that you had fun with this project. So if you create variations on this one, if you can use different colors, make sure to put your versions in the chat. With this, I'm saying thank you for watching, happy coding, and see you next time.